Now for this problem, 4.54, we're going to assume that x is normally distributed. Okay, so we've got our usual normal curve. My usual bad drawing. With a mean of 10. So here's our mean, standard deviation of 2. So determine the value of x that solves for each of the following. For the first, we need the probability that whatever our random value is, x, is greater than some set value, has got to be 50%. So we can already tell, if you want to just look at it, we know that if this is the mean, then there's half of what we've got is above that value. So common sense tells us that this x has got to be 10. But we can solve for it also by just saying that the probability x is greater than some set value of x is equal to the probability that z is greater than some value x minus 10 over 2, right? We've plugged in our magic formula, and here's the magic formula. We'll put that in. Z is equal to x minus mu over sigma. And that's just what we have right here. And then we can say that x minus, well, if we look at the z value, this probability has to be 0.5. The z value affiliated with an area of 0.5, right, on either side there, I'm going to take that here, is going to be z is equal to 0. So if that's the case, then we plug in and just say that x minus 10, oops, I'm mixing my colors here, is equal to 0, and x is equal to 10. And that gives us the same answer we got up above here through common sense considerations. Now for part B, we want to find that the probability that the random variable is greater than some set value x is 95%. So in other words, we've got to be down here somewhere. There's going to be some x here, and 95% of the values are going to exceed that. What is that x? Well, we can easily find the z for that. And we can find that by, well, we know that on the other side there's going to be 0.05. So, what z value is associated with 0.05, that area? Let's look over here. We've actually done this before, so it's 0.05 right in here, between here. So it's about minus 1.601234.5. So we'll call it minus 1.65. Okay. Z is equal to minus 1.65, and we want to see C. And for that one, we're supposed to find the value of x such that the random variable itself can range between x is 10 and some unknown x right here. But this value, all of this, should be 0.2. Well, you already know that everything to the left of 10 is going to be 0.5. So that automatically means that this, and my dimensions aren't very good, this has got to be 0.3. so that 0.3 plus 0.2 is 0.5. So we're looking for the x that's affiliated with an area less than that of 0.3. Now, again, if we pull up our little chart and we look, we can find an area of, let's see, we want something that's a little bit bigger. 0.3 should be right around here. Let's see, around 0.3, it's something like minus 0.5012, minus 0.52. It's pretty close. So, all right, minus 0.52, and now we've got that x value, and we've got that z value. We want to find how that z is affiliated with the x, so we plug it into our formula. Minus 0.52 is equal to x minus 10 over 2. Solve for x, and you should find that x is equal to 8.96. So there we go. So these are actually not bad to do at all. Okay, for the next problem, why don't you go ahead and pause this and take a read of this, and I will, meanwhile, after you've paused it and come back, I'll work part A. So we want to determine the standard deviation of this distribution. The easy way to do this is just to remember again our magical formula. So we've got x minus mu over sigma. So you're thinking, well, now wait a minute. If we're going to set things up with this formula, let's see, we can say that our mean, they give us the mean, it is mean of 159 is our mean. So I'm setting up this equation, and that is equal to, and then we can say sigma, we don't know. X, we actually do know an x, because we can say that we're dealing with the idea that 200, that this value right here, 200 milligrams per deciliter, we happen to know that, I'm going to erase this, that this is equal to a z value that's affiliated with the area of 4.1%. I'm trying to, this area right here, it's the z value that's affiliated with that area. So I jumped ahead here, drew this out for you. You can see here's the mean. There's 200 milligrams per deciliter, and we know this area right here, all of this stuff has got to be 0.841, that area. So this z value for 0.841 should be this z value right here. So let's go look on our table. So we're going to look for the value of 0.841, and that's 0.841 is about 1.00 on the z scale. So that's nice and easy to remember. So we'll say that z right here is 1.0, okay, because that's what that is. So now all we have to do is rearrange and solve for the standard deviation. So we can do that, and we should find that standard deviation is 40.8582, if you really want to take it way out there. Now for part B, what are the quartiles of this distribution? So what is the x value below which is 25% of the area and 75% of the area? Well, this is going to be pretty darn easy. we're actually looking for this x value below which is 25%, 5%, or 0.25, and we're looking for the x value below which is altogether 75%, or 0.75. So all we have to do then is find the z values affiliated with 25%. So I'm going to write this one z 25%, and we will look that up. Okay, we've got 0.25 right here on our table, so it's minus 0.6, 0, 1, 2, 3, 4, 5, 6, 7. It's about minus 0.67. That's on our z table, right? There's the 7 right there. So we've got, oops, minus 0.67 is our z, and now we can just plug that into x minus 159.2 over, and we solved for our sigma before, so it's 40.85, and well, 82 if we want it, and then we can solve for the x, and the x for the 25th percentile is going to be 131.6452. Now we have to do the same thing for the 75th percentile, and I think you can pretty much see what's going to happen. Z of the 75th percent, right? I don't know if that's exactly what you should say, but let's go look right here. 75.75. There we go. 0.75. There we go. So it's going to be 0.67 or 0.68, something like that. Oh, well, gosh, they match. 0.68 on the other side. You know, we're doing a little bit baguesse and bagosh. X minus 159.2 over 40.8582, and all that is equal to, has an x, I guess I'll erase a little bit here, erase a little bit, and we have a solution. X is equal to 186.7548. So there's 75th percentile, and here is the 25th percentile. Now, for part C, what is the value of the cholesterol level that exceeds 90% of the population? Well, that's just not very good English, so we're going to say that is larger than that of 90% of the population. So, in other words, we want something that is, we want to find this z value, which has 90% of the values are below that value. What is that z value? Let's look it up real quick. Okay, so we want an area here of 0.9. Should be right around here. And in fact, it is 1.29 is pretty close. So z is equal to 1.29. Plug that into our equation of z is equal to x minus mu for sigma. So we'll say 1.29 is equal to x minus 159.2 over sigma of 40.8582. Solve for x, and it should be 211.5550. So now, what is the value? An adult, actually we want to do, an adult is at moderate risk if a cholesterol level is more than 1 but less than 2 standard deviations above the mean. What percentage of the population is at moderate risk? So if we wanted to, we could just say the area involved with z is equal to 2, or 2 standard deviations above the mean, minus the area of 1 standard deviation above the mean, or z is equal to 1. Well, if we look up both of those values on our table, we can say v at 2, let's look them up. I gotta move around a little bit. 2.0. Okay, here's 2.0 is 0.9772. So we'll put that 0.9772 minus value 1. So go back here and let's see, value 1 is 0.8413. 0.8413, and when we subtract that out, we have around 0.1359, and that is the percentage of the population at moderate risk according to that criterion. Now let's move on to talk about some of the other different distributions that are available. There's the gamma distribution, and this distribution is very useful for distributions that are not modeled with symmetrical distributions. You can see it's sort of lopsided. In fact, it can be very lopsided depending on what kind of alpha you provide as a parameter in this particular equation for the probability distribution function, which is, or density function, which is that of the gamma distribution. So here this looks immensely complicated, but it actually isn't that bad. This is the standard gamma distribution if beta is equal to 1, and if alpha is equal to 1, then the gamma distribution actually becomes the exponential distribution. Note, sometimes there's a slight variation in terminology of what's used. As long as you just remember these kinds of relationships, that can help you keep track of everything. So, as far as definitions go, for any value of parameter, alpha is greater than some 0, the gamma function is given by this integral. But here's the thing you really need to remember. Whenever you see gamma of some number, actually, via integration by parts, what it ends up being is just this gamma of n is equal to n minus 1 factorial. That's really neat, and it's very handy. We've also got this relationship, which is really quite interesting and I think pretty beautiful. So anyway, what is this distribution good for? Well, it's good for modeling waiting times. For instance, in life testing, as you can see, here's our little tag to toe. We're doing some life testing. The waiting time until death is a random variable which is frequently modeled with a gamma distribution. So the expected value and the variance are given by these nice handy formulas. And here's our standard gamma distribution. You can see it's nicely laid out here. The probability density function is skewed, not symmetric like the normal distribution, and many physical systems are going to have this kind of skewed distribution, so that's why it can be so handy. Now we talk about the chi-squared distribution. we're just going to take a quick look at it. You'll learn more in more advanced courses. It's a special case of the gamma distribution, and alpha is equal to nu over 2, where nu is any positive integer, and beta is equal to 2. So this is important for hypothesis testing, and we'll introduce you later to hypothesis testing. The Weibull distribution, if it has, well, this is the way you would write it mathematically. Here's how it looks, depending on how you fix those parameters alpha and beta. And there are many physical systems, again, where the Weibull distribution fits the observed data very well. Here you see the cumulative distribution function associated with the distribution. Why do we use it? It's often used in life data analysis due to its flexibility. It can mimic the behavior of other statistical distributions. And if the failure rate decreases over time, then we can set the parameter k less than 1. If it's constant, it's equal to 1, and if it increases over time, then k is greater than 1. So here's a few more Weibull factoids. What happens if you have a decreasing failure rate? That would suggest that you have infant mortality, right? That more things are going to die when it's young, and defective items fail early, and the failure rate decreases over time as they fall out of the population. So I think that's very much related to this k is less than 1. A constant failure rate suggests that the items are falling from random events. So that's like k is equal to 1. And if it increases over time, then k is greater than 1, and that suggests that parts are more likely to fail, they're wearing out as time goes on. So again, exponential distribution when k is equal to 1, and when k is equal to 3.4, actually, this distribution becomes very similar to that of the normal distribution. So it has a bucket full of uses, and that can include manufacturing delivery times and industrial engineering. It's also used in weather forecasting, reliability engineering and failure analysis, radar systems, and modeling fading channels in wireless communications, insurance claims, and also wind speed distributions, because the natural distribution often matches the Weibull shape. The distribution, the expected value, and variance are given by these nasty looking formulas, but again they're actually more like plug and chug, particularly if you remember that this gamma of whatever this r is actually is but r minus 1 factorial. That's all that is. So the Weibull distribution, if you integrate it, you'll find the cumulative distribution function. And if you'll remember, the Weibull distribution itself looked really very difficult. But once you integrate it, it actually isn't bad at all. And in fact, you can just plug values in. So let's see how we can do that. The next example. This one deals with steel that exhibits cold brittleness at very low temperatures. This is precisely the phenomenon that the Titanic fell prey to. It's observed that steel's ultimate tensile strength has a Weibull distribution with alpha is 0.01 and beta is equal to 1. So if we let the random variable be the ultimate tensile strength, we're supposed to determine the probability that our x will fall between 98 and 102. So if we're doing that, we're actually just calculating this, the probability that 98 is less than or equal to x is less than or equal to 102, and that is the cumulative distribution function at 102 minus that of 98. And all we have to do is use that previous formula and plug things in. I'm going to see if I can, I guess I can't. So let's see. So here's our formula. It's just f is x equals 1 minus e to the minus alpha x to the beta. So we're just going to plug in there, and that's for x is greater than 0, and of course it's 0 elsewhere. So we'll plug that in and we'll find, well, let's see, it's going to, this first part is going to be 1 minus e to the minus 1.02 to the 20th, and then take that, it's going to be minus 1 minus e to the minus 0.98 to the 20th, and then all that should become 0.513 minus 0.226, and that should be 0.287. So it's actually nothing like as hard as you might think. Here's the beta distribution, and if a random variable has this beta distribution, then its probability density function is just given by this rather obnoxious looking formula. And here's your parameters that you can vary to change its shape. Again, you see this gamma of alpha or whatever. It's called the standard beta distribution if your parameter a is equal to 0 and b is equal to 1. And this probability density function is positive only on a finite interval. So it's not for all x is greater than or equal to 0. Here's your standard beta distribution right here. And you can see by varying your parameters, you can get all sorts of interesting shapes. And if alpha and beta are 1, then this distribution reduces to the uniform distribution. So here's the expected value and the variance, right? Just these common formulas. And it's commonly used to model variation in the proportion or percentage of a quantity. So you could say it's variation in the proportion of a 24-hour day that a person's asleep, or the percentage of an element in a chemical compound. So other distribution applications might involve PERT charts. A standard assumption in PERT sort of analysis is that the time needed to complete any particular activity once it started has a beta distribution, with events A is your optimistic time to finish and B is your pessimistic time to finish. And so let's go ahead and work a problem that relates to this idea. So here's our conveyor system. A is equal to 2 days, B is equal to 5 days, alpha is 2, beta is 3. First let's draw we know that the probability that x is less than or equal to 3, if we have this distribution, is, well, we're integrating from A, right? That's our starting point, can't be less than that, to 3 days, and we'll say gamma alpha plus, that's gamma right there, sorry, alpha plus beta all over B minus A over gamma alpha, gamma beta, and then x minus A 2 over B minus A. And this is to the alpha minus 1, and then, oh, I hope I can squeeze this in here, B minus x over B minus A, and all of this I'm going to write the exponent to the B minus 1 on the top there, and then it's at the very edge, which is going off the edge, is dx. So we're integrating. So we're going to take this and we're integrating from, well, what's A? A is 2. So I'll write 2 here. And alpha plus beta. Okay, so we have alpha plus beta is 5, so that will be gamma of 5 factorial, and gamma of 5 is equal to what? Gamma or 5 minus 1 factorial, which is 4 factorial, which is 4 times 3 times 2, which is 24. So we've got 24 up here, and then down here we're going to have, well, let's see, b minus a is going to be 5 minus 2, which is 3. Gamma of alpha is going to be gamma of 2, which is going to be 2 minus 1 factorial, so that will just be 1. And then gamma of beta is going to be, well, beta is 3, so it'll be 3 minus 1, which is 2, 2 factorial, which is just 2. And then plugging in these values over here, whoops, make that clear. So we've got x minus 2 over 3, and then here is going to be 5 minus x over 3. Oh, and alpha minus 1 is just 1, and beta minus 1 is going to be 2 to the dx. So now we can say this is all going to be equal to, well, multiply all that out, it's 4 over 27, right? Because remember, take these this 3 and this 3 squared, right? So all of that's going to come out over here too, so that's why it ends up being 4 over 27. Integrating 3, 2, and it's actually going to be, when you multiply everything out, it'll be x to the third minus 12x squared plus 45x minus 50 dx. And when you work that whole integral out, you should get 0.407, right? So that's all there is to that problem. Now if you look at example, and notice this is example, so it's within the textbook itself, not within the problem sections. It says a binomial random variable models the error where the probability of error is really, really small. What is the probability of 150 or fewer errors, 16 million transmitted bits? If you did this right, this is sort of like a coin toss with a really, really small probability of getting, say, heads. So what we would have is we'd have 16 million coin tosses. Choose, well, if we wanted 0 errors, we'd say 16 million, choose 0. Use the rest of the formula for the binomial distribution here. And we'd have to take that and do it for 0, and then 1, and then 2, and 3, all the way up to 150, and then add that all up, and we would find the probability that x would be, you know, between 0 and 150 errors in 16 million transmitted bits. Well, this is really a cumbersome thing to do. So the idea here is that this binomial distribution can actually be approximated by the normal distribution, and you can see right here that they can approximate one another. And if that's the case, if we do that, then all we need to do, if we know the parameters n and p for that binomial random variable, we can figure out what the z-score is by just using this formula, and then we can figure out probabilities by plugging values into these formulas. So in that sense then, we can say that the conditions for approximating hypergeometric and binomial sorts of probabilities are as follows. If the number you're selecting out of the whole larger number is less than 0.1, then you want to use the hypergeometric distribution. On the other hand, if NP is greater than 5, right, then you'd want to use the normal distribution. And for anything in between, you'll use the binomial distribution. Now we suppose that we have x is a binomial distribution variable with n is equal to 200, p is equal to 0.4. We're supposed to make these approximations that x is less than or equal to 70 and so forth. Now we want to remember that when we are dealing with binomial random variables, we calculate the mean as just n times p, and that's what you see here. And then this is n times p times 1 minus p, or q, and that's what you see here, and that's how you calculate the variance. And of course, the standard deviation is just the square root of that. So now we've got with these values actually calculated out, the mean and the variance, so and standard deviation. So now probability for part A, that x, the random variable, is less than or equal to 70. We can calculate that out by saying it's the probability that x is less than or equal to 70, which is approximately equal to the probability that z is less than or equal to, and it's 70.5 because we're actually going on the upper part of one of those boxes, and 8 minus 80, our mean, over square root of 48, and that's equal to, well, go down here, probability that z is less than or equal to minus 1.37, and that, as it turns out when we read our table, is just 0.0853. So that's the probability that x is less than or equal to 70. Makes sense since the mean itself is 80. Now, going on to part 2, approximate the probability that x is greater than 70 but less than 90. So what we're really looking for is this probability, which is about something like probability that 70.5 minus 80 all over square root of 48 is less than z is less than 89.5, oops, 0.5, come back here, minus 80 all over square root of 48, and we'll put a little bracket there, and this is actually going to be the same as the probability that z varies from minus 1.37 to 1.37, and when you plug in the actual numbers, the area affiliated with that z is 0.91466. That's the first z. Oops, no, that's the second z, sorry. And then minus 0.08534. And when you subtract those, it becomes 0.8293. And that's the probability. Now, we approximate the probability that x is equal to 80. That's just the probability of 79.5 is less than x is less than or equal to 80.5. And that is approximately probability that z ranges from 79.5 minus 80. We're calculating a z value right there. Little do you know, it's less than z is less than or equal to 80.5 minus 80 all over square root of 48. And that means that z varies from minus 0.07217 less than z is less than or equal to 0.07217. And that, in turn, is 0.0575. Voila! Okay, oops, I added that back there. Okay, so now let's go to our final problem. The time of arrivals of small aircraft at a county airport is exponentially distributed with a mean of 1 hour. What's the probability that more than 3 aircraft arrive in an hour? So what we'll do is we'll let y be the number of arrivals in 1 hour. And if the time between arrivals is and lambda is equal to 1 is the arrival per hour. 1 arrival per hour. That's our lambda. So for A, then, we can say the probability that y is greater than 3 is actually going to be 1 minus the probability that y is less than or equal to 3. And that will be 1 minus, well, just applying the Poisson, e to the minus 1, 1 to the 0 for 0 factorial, plus e to the minus 1, 1 to the 1 for 1 factorial, plus e to the minus 1, 1 to the 2 over 1 to the 2 over 2 factorial, plus e to the minus 1, 1 to the 3 over 3 factorial, and when you calculate all that out, it's 0.01899. Okay, so we've got that. So we're going to keep this part right here. So now we've got this probability right here that y is going to be greater than 3. And what we're going to do is we're going to let w denote the number of 1 hour intervals out of 30 that contain more than three arrivals. So by the memoryless property of a Poisson process, W is a binomial random variable with, well, n, we're going to try 30 separate 1 hour intervals. So n is equal to 30 tries. And our p is just the probability of success is this, we calculated it down here, it's 0.018 899. That's the probability that we'd have more than 3 aircraft arrive within that 1 hour. And so then, let's erase here so we have a little more room. And we can then say that the probability that we will have no intervals with that have more than 3 arrivals is 30, count them, 30, choose 0, and then we've got our p.01899 raised to the x power, which is 0, and then q, which is 1 minus p, 0.01899 raised to the 30th power, and all that computes to be 0.5626. So this is very nice juxtaposition of the binomial, and then showing how the binomial intersects with the Poisson, or how those two ideas or distributions are related to one another.